All right, the next one is a 10 to the 5 gigabecquerel source, which from last time is 10 to the 14 photons per second. This is a 1 MeV. Is uniformly distributed within the volume of a hypothetical sphere of 2 meters in diameter entirely within a water medium. So same problem as before, except now it's distributed through the sphere. I'm not going to draw the other lines on here. But this is 1 meter. Let's just say that this is R out to some distance. So we need to find all these different values. So we have to break this up into small pieces because there's source all the way through here. So we're going to say that this sphere is made up of a bunch of infinitesimal, very thin. I can't say it's
infinitesimal.
Infinitesimal. Is that how you say it? Infinitesimal.
Just differential.
There you go. Differentially thick shells. All right, of thickness R. So we want to let's find the area source per area in this thing. So, or source per volume. So source per volume, 10 to the 14 photons per second over 4/3 pi R cubed. And this gives 2.39 times 10 to the 7 per centimeter cubed per second. So this is a volume source strength. So that means that all the volume inside here is emitting this many per centimeter cubed per second. So now we need to find the source strength of a small shell. So first we're going to find this. This will be nice and easy first. So we're going to take one of these shells and we're going to say that it has thickness dr, and this is actually a spherical shell, so it's going to have area is going to be 4 pi r squared. So the volume of one of these shells is going to be 4 pi r squared dr, and the source stored within that sphere, source strength is going to be SV times 4 pi r squared dr. Everybody okay with that? Source strength for that shell, because this is going to be in units of centimeter per centimeter cubed per second, and whenever you integrate this, you're going to get r cubed, and so this is going to be centimeters cubed, and so you'll end up with photons per second. So we'll write some differential flux you're going to get from one of these things is going to be SV 4 pi r squared dr over 4 pi r squared times e to the negative mu r. So everybody okay with that? You have your geometric attenuation and exponential attenuation. So these cancel out, making your life nice and easy. So dV equals SV e to the negative mu r dr. And we're going to integrate both sides. So you get phi, and we're going to integrate this from 0 to let's call this big R. So SV, so SV is a constant, SV 0R e to the minus mu r dr. You end up with 3.38 times 10 to the 8 per centimeter squared. per second. Is everybody okay with how we found this? 10 to the 8, yes.
So, like, if it were a test, like, you could do the kind of the same thing on this one like you did in the last one, right? Just say it's like a point, and you're moving R just as a point source, moving closer to the detector.
Yeah, you can say that this was a line source.
That's essentially what doing that interval did.
That's what I'm saying, but like during a test, would he be okay with you just saying,
Oh
okay?
yeah, he loves that stuff.
Okay, alright, I
All
wanted to
his
make sure.
problems are made like
So
that.
you could do that?
Yeah.
Okay, fair enough.
All his problems, I mean, in the book,
There's
all
always
his problems
Yeah.
are based upon. I was saying that this is a line source across here. So you take this and divide it by, you get SL equals 10 to the 14 over R, and you get some value per length. And then you'd say that the differential flux is equal to SV, or SL, I'm sorry, SL dx over 4 pi x squared e to the negative mu x, and integrate from 0 to R. Taking a thin piece of that line source right there. You get the same value. Dr. Schultz likes the symmetry of problems. Makes it an art. Alright, next is you gotta find exposure. And I'm not gonna do that because it's really easy and it's the last problem. It's the exact same response as the last problem. Response function, this last problem.
But then what about the build-up factor? Is that going to change?
Yeah.
Okay.
Oh yeah.
Sorry, just making sure you weren't going to the next question.
Yeah. Next one is that E? Is this part E?
Yeah. Yeah. E. You go A, D, and E.
Okay. All right. So for part E, we want to find exposure, which is not easy as last time. So we're going to do a similar thing. This is including buildup. So we're going to take a differential exposure is equal to the response function for the exposure. And then we're going to get some value from uncollided. And it's going to be the same as last time for uncollided. SV 4 pi r squared dr. So this is your photon strength per shell over 4 pi r squared. So these cancel again. So it's geometric attenuation. E to the negative mu r. This is your exponential attenuation. And you're also going to have some buildup factor. And we use Berger for lots of stuff, so this is some function of energy and mu r. Now, if we're going to integrate over both of these, we get exposure is equal to integral of r sub x SV dr e to the negative mu r buildup factor, which is some function of energy and mu r. And until you actually plug in values before you integrate and everything, leave this notation on here so you don't mess up. And you're going to integrate from 0 to big R, 1 meter. So what in here is so this is constant. This can come out. Can anything else come out? dr, that stays in obviously. Rx, that can come out. E to the negative mu r, that has r in it. You can't pull that out. B, you can't pull B out because B is some function of r. So you have to leave that in there. Okay, very important to leave that in there because the buildup factor is going to change however far away you are. And there's points on this test, that's why Harvey on it. So, plugging in our Berger value, we're going to have x is equal to SV r sub x 0 to r dr e to the negative mu r 1 plus a mu r e to the b mu r, right? And we have, let's go ahead and integrate that. We can, or let's distribute and integrate. So this first one is this first term is pretty simple. That's just going to come out to, what is that? Negative 1 over mu e to the negative mu r plus integral a mu r e to the mu r b minus 1 dr you gotta do the integration by parts. I'm not doing that. I'm gonna tell you what you can get. Unless somebody wants to do integration by parts for me real quick. Oh gosh. Okay, so you get all this, and you got to plug in values, and plug in those values. Equal to 0.4488 bar per second. Make sure this is right.
Is that a beta minus 1 up
What?
next to your E on the right hand side? Or both?
B minus
Sorry.
1, yeah, B minus 1 mu r.
Okay.
Yeah.
I'm a Boy Scout, okay. Shut up.
So this mu cancels with that mu and that squared. R plus 1 squared, A, okay, yep. Okay, anybody have any questions on this one? This would be way different if we had said that B was the constant. It'd be way different. It'd be wrong. Alright.
Good.